Well, thanks, first of all, to the organizers, and thanks for the introduction. So as mentioned, this project is in collaboration with Ericsson, and it basically arose from a PSI winter school at Perimeter Institute, where you do like a week of theoretical physics. And between me and David, we managed to put out this work, and it sort of looks at Unruh detectors in the context of gravitational shockwaves. So this conference has explored Unruh detectors and other things from maybe a bit more of a formal point of view, but this is sort of maybe a cute example of the power of them. So to start with, I want to go through basically the memory effect and asymptotics and symmetries in GR and how that relates to gravitational shockwaves, and then talk about these Unruh detectors and the entanglement harvesting protocol, which will then allow us to talk about shockwave detection and harvesting in the context of these Unruh detectors. So very briefly, the gravitational memory effect is basically if you consider a perturbation on a space-time which satisfies some wave equation, you can end up with a permanent displacement of this perturbation. And that sort of is something that we are hoping to see, at least in the near future. And this has some connections, at least to asymptotic symmetries. But what we want to be talking about here is really the vacuum state of quantum fields in a bulk spacetime. And this gravitational memory effect has some nonlinear features as well, but we'll mostly be talking about in the particular context of a shockwave. So what does this relate to asymptotically flat spacetimes? Well, in asymptotically flat spacetimes, you have essentially boundary conditions and fall off such that you get a nice expansion of your metric, which looks like flat spacetimes plus some higher order corrections. And all of the asymptotic data is encoded in these sort of extra corrections to flat spacetime. And in particular, they allow you to talk about the mass of your spacetime, the angular momentum, and then you have two other objects. One is the shear tensor and one is the news tensor. And the news tensor is essentially what has these gravitational waves, but the memory effect is actually encoded in the shear tensor, and you can have a sort of non-zero difference between this corner of your asymptotically flat spacetime and this corner. And recently, that has sort of been connected to these asymptotic symmetries, which are the symmetries which preserve your metric far away. And it turns out that this symmetry group is not just the Poincaré group. You get this additional feature called supertranslations, which essentially can be understood as generating some additional shear, that is some additional memory effect on your spacetime. And essentially they look like an ordinary translation in the time direction, but this function now depends on the angular coordinates of your metric at the boundary. So it sort of has not just one translation, it has an infinite number of them. And in some sort of zero energy limit, these generate shear and lead to vacuum degeneracy of the gravitational spacetime. So that is that two gravitational spacetimes are distinct if they have a distinct shear. And this supertranslation sort of allows you to go between these different spacetimes. Recently, this has been sort of proposed as a mechanism for storing extra information on black holes. And one question is, how do you physically implement a supertranslation? And one way of doing this is through these linearized shockwaves, which I'll talk about. And in this context, people were trying to understand, do these bulk shockwaves, these linearized shockwaves, leave imprints on quantum fields that live on this background spacetime? And there are a couple of results that suggested that they don't really affect vacuum state situations. But we know from some work by Smith and others that linearized gravitational waves do affect vacuum entanglement. So there's a sort of disparity between these two things. And my claim is that shockwaves do affect vacuum entanglement too in a particular context. So the main motivation is that if we want to talk about these signatures of supertranslations, they need to be in a physically extractable way. So like often they're encoded in classical things like the memory effect, or they're not immediately observable. So they're in Bogoliubov coefficients or soft factors. One way to get around this is to use an operationally sensible protocol, which is governed by this entanglement harvesting procedure, which we'll talk about in just a second. But first, I want to talk about the particular spacetime, which is this gravitational shockwave. And essentially, it's a gravitational wave that only travels along one null coordinate. And of particular importance is that the stress energy tensor is very simple, and the energy density of this wave is controlled by this profile f of x. So it provides a nice simple example where you can do some explicit calculations. Why is this related to supertranslations? Well, it turns out that you can see it effectively has something like a memory effect. By performing this coordinate transformation, you end up with a metric that's essentially the Lie derivative of a flat metric. And the vector by which you're translating it is exactly proportional to this function f of x, which was the profile of the shockwave, which determined its energy density. And in particular, you can see this is very, very reminiscent of these angle-dependent translations, these supertranslations. So that's sort of the connection here. Now, quantum field theory on this spacetime was studied a long, long time ago. And it turns out that if you treat a massless scalar field on this background spacetime, there are two standard mode decompositions. One you can do on before the shockwave passes, and one that you can do after the shockwave passes. And it turns out that these two vacua that you can define are naively unitarily inequivalent. That means that you don't see any particle production going on. It's sort of a very boring spacetime, which would suggest that, as said, these shockwaves, which are sort of related to these supertranslations, don't leave an imprint on quantum fields in this situation. But what I want to draw attention to is that this number operator is essentially a global definition. It doesn't really represent what local observers might see if they're interacting with the quantum field. So the way that we want to talk about this is to essentially use these Unruh DeWitt detectors, which are an idealization of the light-matter interaction, where you have some sort of two-level system that interacts with the scalar field linearly. And for ease of calculation, I'm going to sweep all subtleties of a point light detector model under the rug and just proceed. So in particular, the idea is that if we have two observers, Alice and Bob, who live on either side of the shockwave and only interact with the field when it's completely flat spacetime. Remember that the metric is flat on this side and on this side. The question is, do they see anything? And basically you start with an uncorrelated state of Alice, Bob in the field, and you evolve under this Unruh DeWitt interaction and then trace out the degrees of freedom of the field. And you're left with a correlated state. And the question is, what do these correlations look like? And this is a well-studied problem. And generically, the density matrix will take this form, where PA and PB represent the excitation probabilities of Alice's and Bob's detectors individually. So that's the probability that they transition from the ground state to the excited state, i.e. they see something. Then the off-diagonal terms turn out to be non-local, in that they correspond to both Alice and Bob's trajectories, and they correspond in particular to the Whiteman function along these trajectories. So what you can do is you can quantify the entanglement structure that's generated by this particular map through whatever entanglement measure you like. And one example is concurrence, which, as you can see, depends on the off-diagonal terms, M, and also the local excitation probabilities. So very briefly, what you can do is you can consider a detector which just one detector for now, which crosses the shockwave, and you can ask, does that see the shockwave happening? And it turns out the answer is yes. And you can see this in this plot because for different kind of shockwave profiles listed below, there is a deviation from the flat space response, which is denoted by the dotted line. And this increases with increasing the strength of the shockwave. This is actually in contradiction to what these people found with linearized shockwaves. And it turns out the way to reconcile this is that linearized shockwaves are only valid to a first order correction in the Whiteman function. And if you have sourceless shockwave, you get a similar result where the first order correction basically vanishes. However, if you go to the full nonlinear picture, then one detector can see this shockwave. Moreover, if we go back to the original scenario where we imagine Alice and Bob on either side of the shockwave interacting for a period of time, it turns out you do see some concurrence. So you see enhanced entanglement between Alice and Bob. And so the way to understand this picture is to imagine that you position Alice somewhere and Bob somewhere else. And the dashed line here represents where Alice does not cross the shockwave, but the gray line also represents where Alice and Bob are not space-like separated, so they can just ordinarily communicate with each other. So this zone is not very interesting. This intermediate zone is where Alice crosses the shockwave, which we know from before causes her to have a excitation transition. So that's also sort of not really interesting. But there's this little zone here where Alice never crosses the shockwave, and still her and Bob become entangled through the quantum vacuum. And so even despite this being almost like flat space for both Alex and Bob's situation, you actually do get this detection and extra entanglement due to a gravitational shockwave. And this is what we call the quantum imprint of a shockwave. So very briefly, to summarize, I have essentially reviewed the memory effect and asymptotic symmetries and how they relate to these gravitational shockwaves. And I think the takeaway from this is that local observers can see things, particularly if you have multiple local observers, they can see things that are not necessarily visible to the global state. And that is one way of understanding that these vacuum states of shockwaves contain information. And I think what this kind of leads to, and Erickson will talk a little bit about in the next talk, is basically, can you understand this kind of phenomena where you see like the effect of a gravitational shockwave or the radiated data of gravitational degrees of freedom enter into scalar fields living on top of that space-time? And can you understand that in a generic way? And if you're just living asymptotically away from whatever happens. And so that's sort of one ongoing thing that we want to think about. Thanks.
So thank you very much, Finnian. Questions? No questions?
Yeah, I'll ask about the other vertex of the infrared triangle with respect to soft particles. Can you tell me what these insights might contain for that?
Well, I'm not sure it's directly translatable. There was a talk earlier on today about can a detector see these soft modes, and essentially there that looks at dress state. So maybe if you considered a dress state, that might tell you something more about that. I think my perspective, our perspective is basically this is a sort of orthogonal line of direction to that, but it sort of probes related concepts.